Hi, welcome to the third session of the theory of the firm. My name is Elias. In this video, I will take you through the long-run production process and look at a situation where the firm has the capacity to alter all the inputs brought into the production process. This means that in the long run, there are no fixed factors. The firm is able to alter or to change all the inputs, bring in new inputs or remove some of the inputs that it has in the production process. Okay, so this is the long run part 1. We're going to have a long run production part 2 and part 3. So they've been broken in such a way that they will help you understand what happens in the long run. So these are phases of the production process. So we'll begin by first looking at the general production function. Okay, so consider two inputs, that is capital and labor. Then the long run production function can be written as the function of capital and labor, where this time around capital has no bar on top of it to mean that we are in the long run. Remember that when we were in the short run, capital had a bar here to indicate that capital was fixed. But in the long run, capital and labor are all variables. So therefore, we are able to change their amounts during the production process. Okay, so with that then, this would imply that output will change when both inputs are changed. That is, if you change capital, or if you change labor, or if you change both capital and labor. Okay, so now the long run production function is represented by isoquants, which are also known as the equal product curves or the production indifference curves. Now, they are so-called production indifference curves because their structure is similar to those that we saw during the time we're looking at the consumer choice theory, which are the indifference curves. So in other words, even isoquants are convex to the origin and they are downward sloping. So we'll look at the features later. For now, let's build the theory. So an isoquant shows the different combinations of two variable inputs which produce an equal quantity of output. In other words, an isoquant is a locus of points that shows a combination of two inputs, capital and labor, that yield the same level of output. So the firm is able to alter the amount of capital and the amount of labor but still remain on the same level of output. If the firm is producing 50, it will alter the inputs but still produce 50. That is what an isoquant is. Let's look at the graphical illustration. So on the vertical axis we put capital and on the horizontal axis we put labor. With the isoquants 1 and 2, you will notice that this is the same structure we saw under indifference curves or theory of the consumer. Now what this means is that the red isoquant has more output level compared to the black isoquant. But all points on the red isoquants have equal output and those on the black isoquant have equal output. So A, B and C have equal output but less compared to D and E. With that said, then a higher isoquant refers to a greater quantity of output and a lower one refers to a lower or smaller quantity of output. With this then, given the three isoquants, the black, the red, and the green, it means that the green isoquant has more output level compared to the red and the black. In other words, put in the visual illustration, isoquant Q1 has lesser output compared to Q2, and Q2 has lesser output compared to Q3. Therefore, the direction of increasing output level is up and to the right. From the production function, Q being a function of capital and labor, which is the two input example, we can find the marginal product of capital and the marginal product of labor using the derivatives. Now, you recall that when we are finding the derivatives, we get the rate of change of the output brought about by some rate of change in the input brought into the production process. With that, we can find the marginal product of labor as dQ dL, meaning change in quantity brought about by the change in the labor. In the same way, we can get the marginal product of capital as the change in quantity divided by the change in capital. With that then, marginal product of labor simply declines as more labor is applied, and also we should note that the marginal product of capital declines as more capital is applied. This means that the law of diminishing marginal returns holding one factor constant still holds when you are employing more with reference to the other factor. That is, if you hold capital constant or you hold the employment of capital but continue bringing in labor, the marginal product of labor will be declining after a given point. Therefore, marginal product of capital and marginal product of labor decline as you employ more and more and less of the other. Let's now look at the marginal rate of technical substitution, which is the slope of the isoquant. Now, the marginal rate of technical substitution is the rate at which the factors of production can be substituted at the margin without changing the level of output. If you recall, when we were looking at indifference curves, we noted that the slope of an indifference curve was called the marginal rate of substitution. But in isoquants, because we are looking at the production techniques, we put the word technical in the middle so that it becomes the marginal rate of technical substitution, and that is the substitution of the techniques that are brought into the production process. That is the combination of labor and capital that will produce a given output. So at the when we draw our isoquant, we can call this isoquant our Q1. So if we have our isoquant Q1 and we draw a tangent, a line that will be tangent to the isoquant, at the point of tangency, that point is the slope of the isoquant. If you draw your tangents, your tangent here, and the line become tangent to the isoquant at this point, it means that the slope of the isoquant will be measured here using the marginal rate of technical substitution. So, simply put, the marginal rate of technical substitution is the slope of the isoquant. We can have further descriptions of the marginal rate of technical substitution. It is the marginal rate of technical substitution of labor for capital is the number of units of capital which can be replaced by 1 unit of labor without changing the level of output. In other words, we want to know how many units of capital are we going to give up for us to bring in just 1 unit of labor and leave output level unchanged. This describes the slope of the isoquant. Now, in other words, it is the amount of capital that a firm can give up by increasing the amount of labor by 1 unit and still remain on the same isoquant. With this then, we can measure the marginal rate of technical substitution of labor for capital as the change in capital divided by the change in labor. Now, if you wanted to find the marginal rate of technical substitution, marginal rate of technical substitution of capital for labor, this will be, we interchange these. It means up here we'll have the change in labor divided by the change in capital. So this is the marginal rate of technical substitution of capital for labor. The earlier one, the one we have here, this one here, is the marginal rate of technical substitution of labor for capital, meaning we are taking out capital and bringing in labor. Marginal rate of technical substitution of capital for labor, it means we are bringing out labor and pushing in capital. So you should not interchange these. You should have a clear understanding of the meaning of marginal rate of technical substitution. Okay, so given a production function, a change in output attributed to a change in one of the inputs holding the other inputs constant gives the marginal product of the variable input. Now, simply defined then, that the marginal product of labor, we said it's a change in quantity divided by the change in labor, and the marginal product of capital is the change in the output divided by the change in the capital. Now with these two, we can then define our marginal rate of technical substitution of labor for capital as the change in capital divided by the change in labor. Now, this is also equal to the negative of the ratio of the marginal product of labor to the marginal product of capital. In other words, what we are saying here is that the marginal rate of technical substitution, marginal rate of a technical substitution of labor for capital is equal to the negative of the marginal product of labor divided by the marginal product of capital. So we are putting this negative here to show that the slope of an isoquant is downward sloping. Okay, so let's now put this theory together. So what we have then is that we can now look at the law of diminishing marginal rate of technical substitution. Now, the marginal rate of technical substitution diminishes as more and more of labor is substituted for capital. This, if you did not watch or you did not attend the lecture for the theory of the consumer, I urge you to go back there and have an understanding of the diminishing marginal rate of substitution. So it's the same principle that we are bringing here. So the marginal rate of technical substitution of labor for capital also diminishes the more labor you're bringing into the production process, because that labor will outweigh the capital, and as such the little capital that the firm will remain with in the production process will become more valuable than the labor which is being brought in. As such, the firm will be willing to release less and less amounts of capital for each labor inputs brought into the production process. With that, then, as the firm moves down an isoquant, the marginal rate of technical substitution diminishes, and therefore the rate at which the marginal rate of technical substitution diminishes is a measure of the extent to which the two factors can be substituted for each other. This means that when the marginal rate of technical substitution is very high, it tells you that the firm is able to push in smaller units of labor and release a lot of capital. As the value or the marginal rate of technical substitution becomes smaller and smaller, it informs you that the firm's desire to release capital is less the more the labor is coming in. The smaller the rate at which the marginal rate of technical substitution diminishes, the greater the degree of substitutability between the two factors. Okay, So if the marginal rate of substitution between any two factors does not diminish and remains constant, the two factors are said to be perfect substitutes of each other. And if there is no substitutability at all, it means the two commodities are complements. Let's begin by looking at the perfect substitutes, which are displayed by linear isoquants. Now, in linear isoquants, there is perfect substitutability of inputs, and this means that each of the factors can be used equally well in place of the other. This means if you remove capital and bring in labor, labor is able to do a good job which capital would have done, and therefore output will not be affected. With that, the marginal rate of technical substitution is constant, which tells us that the isoquant is a straight line. From the top left of the isoquant to the bottom right, the slope of the isoquant will not change. It will remain the same because the line is a straight line. The curve is a straight line, or the isoquant is a straight line. With this brief background, then we can conclude on linear isoquants graphically that the direction of increasing output is up and to the right. So this is similar to what we saw in the theory of the consumer. Thus, if the firm's marginal rate of technical substitution is constant throughout the isoquant, then the two inputs, here being capital and labor, are said to be perfect substitutes. Let's turn our focus to the Leontief production function. So in the Leontief production function, this is where we have the L-shaped isoquants. Now in these isoquants, there is complete non-substitutability between the inputs. Why? Because they are perfect complements. That is, they are used jointly for production in fixed proportion. For example, if you have you want to produce, say, maybe a bicycle, which is a classic example brought in here, an increase in one factor without any required disproportionate increase in the other factor will yield no additional output whatsoever. Let me take you to this example. 2 wheels and a frame are required to produce a bicycle. This means that if you want to produce 2 bicycles, you will need 4 wheels and 2 frames. If you want to produce 3 bicycles, you will need 6 wheels and 3 frames. This cannot be interchanged because the proportion is fixed. 2 frames and 1 wheel will not help you make a bicycle. So we should understand the principle of fixed proportion because the inputs will be brought in such a manner and the production will not be substituted. This is known as the Leontief isoquant or the input-output isoquant. Let me give you the graphical illustration. So we have the capital on the vertical axis and labor on the horizontal axis. The direction of increasing output is up and to the right. Now, with the isoquants which follows the Leontief production function, the production will take place at the corner here because anything more will not make sense to the production function. If you have 6 wheels and 1 frame, it won't help you, it won't make you produce 3 bicycles. You'll still produce 1 bicycle. Therefore, the point of activity in the Leontief is at the corner. Anything beyond that will not make any sense to the production process. So inputs that are used in a fixed proportion are called perfect complements. Let's look at the convex isoquants, which are the usual isoquants that we described when we started looking at them in this unit. Now, in convex isoquants, there is substitutability, though not complete. between inputs, and because of this, it tells you that the curve then is convex to the origin and downward sloping. If it was linear, we were going to have perfect substitutability. And if it was an L-shaped, we are going to have non-perfect or non-substitutability at all. But these are in the middle between the linear and the L-shaped. Drawn together, so we have the one that is linear here, perfect substitutes. In the middle, we have the convex, which is somewhat like L, linear L, but forming a curve. And then finally, we have the Leontief, which goes like that. So the possibility or the degree of substitutability reduces as you are moving from the linear to the L-shaped. Or we can say the degree of substitutability decreases as you are moving from the L-shaped to the linear. Okay. For example, a shirt can be made with large amounts of labor and a small amount of machines. The same shirt can be made with less laborers but increasing machineries. This tells you that we are able to substitute inputs here but produce the same level of output, which is a shirt. As such, then, we can look at the general properties of the isoquants, which we take to be the ones that are convex. The first one is that isoquants are downward sloping. This means that if total output is to remain unchanged throughout the curve, more of one input means less of the other. For you to produce more of, for you to employ more of labor, you need to do a trade-off. That is, you need to release capital and be able to produce the same level of output. In that way, you will have a downward sloping isoquant. The second property is that isoquants are convex to the origin, and this means that the slope of the isoquants diminishes or becomes flatter as we move from top left to right bottom along the curve. Now, this is an illustration, so let me do a rough drawing here. So we are in this form. So if you are here, the more you are moving down the curve, you will notice that the curve will be becoming flatter. In other words, the slope will be diminishing, and this gives you the convex isoquant. So the slope of an isoquant, as termed earlier, is called the marginal rate of technical substitution, which is simply the rate at which one input can be substituted for another in the production process and leave output unchanged. Let's look at the third property. Higher isoquants represent a higher level of utility than lower isoquants. Now, this is what we had illustrated earlier, that all output levels are different. One has different output levels, two has different output levels. But for each given output level, all points that are lying on the same isoquant will give you the same output level. So on isoquant 2, D and E will produce the same level of output, but different mixtures of the inputs. Point E on isoquant 2 has more labor and less capital compared to point D on isoquant 2. If you look at isoquant 1, point A has less labor and more capital compared to point C, but yet the output level will be the same along isoquant 1. So this means that these points, point D and E, have higher output levels compared to points A, B, and C. The last property is that isoquants cannot cross each other, and this is because of transitivity that we stated earlier in the theory of the consumer. The reason why this is the case is that if you consider isoquant 1 and isoquant 2, point B and point C are on isoquant 1. Therefore, they have the same level of output. Point A and point C are on Isoquant 2. Therefore, they have the same level of output. So what we've seen is that B and C have the same output, A and C have the same output. But if you look at A and B, A is on a higher isoquant than B, which means that A has more output than point B. Now, if B and C have the same output, and A and C have the same output, this should automatically mean A and B have the same output. So this then contradicts the theory, and therefore we should always ensure that the isoquants do not cross. Okay, so thank you very much for watching. If you have questions, send an email to muauelias@gmail.com. I will share with you the YouTube link that you can use to watch the video when you have some free time. Bye-bye.